Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for n queens puzzle. Let's look at the problem description. The n queens puzzle is a problem of placing n queens in the n by n chessboard such that no two queens are not attack each other. Given an integer n, we have to return the number of distinct solutions to the n queens puzzle. Let's take a look at the example 1. So the number of queens is 4. The chessboard size is 4 by 4. There are two distinct solutions for this input. Okay, the first one is in the row 1 the queen is placed in column 2. In row 2 the queen is placed in column 4. In row 3 the queen is placed in column 1. In row 4 the queen is placed in column 3. This queen is not attacking any queen horizontally, vertically and diagonally, and this also it is not attacking diagonally, vertically and horizontally. This one is also vertically, horizontally and diagonally not attacking others. This one diagonally not attacking others, horizontally not attacking, vertically not attacking. Same way in this solution also, none of the queen is attacking each other. So that's why the output is 2. And in the case of example 2, the number of queens is 1 and the board size is 1 by 1, so the output will be 1. So we can place that one queen in that single cell. The constraints for this problem are the number of queens is ranging from 1 to 9. Let's look at the approach to solve this problem. The number of queens given is 4. For 4 queens, there are 2 distinct solutions available, wherein we can place all the 4 queens in each row such that they are not attacking each other. First, let's see how to place the queen in the n by n chessboard. Okay, we start with placing the queen in the 0th row. Okay, so there are 4 possible cells we can put that 0th queen. We start from this cell or this or this or this. After placing the queen in the 0th row, next we place the queen in the first row. Okay, so here there are 4 possible cells. Okay, after placing in the 0th cell, we can place either one of these 4. After placing here, we can place either one of these. After placing here, we can place either one of these. Okay, so totally how many combinations we have? Totally 16 combinations we can have. We can have 4 combinations that starts with 0, and we have 4 combinations that starts with 1. We can have 4 combinations that starts with 2. 4 combination starts with 3. After placing this, again we have another 4 options. So at each row we have 4 options. So when we complete, totally we have 4 to the power 4 solution at the end. But out of that, some queens placement may attack each other. Okay, so we have to check whether the queens are attacking each other or not as we place the queens in each cell. If the queens are attacking each other, then we do not have to proceed and backtrack. In order to verify whether the queens are attacking each other while we are placing them in a particular row, we need to maintain a slate. Basically in the past rows where the queen was placed. We need that information in order to determine whether the current queen's placement is valid or not. Okay, for example, after placing the first queen, the slate will contain 0 and 2. So each index of this slate is corresponding to the row in which the queen is placed. Value at that index is the column at which the queen is placed. For example, as per the slate, the 0th index, which is the row 0, has the queen at column 0. The first index tells the queen 1 is placed at row 1 and column 2. Okay, so likewise we have to keep track of where the queen is placed in the previous rows in this slate. Okay, with this information we can decide whether the current placement will attack the previous queens or not. If the current queen attacks the previous queen's placement, then we can stop computing the current solution and we can backtrack. We can look at this queen's placement flow as a tree. The 0th queen can be placed at column 0 in row 0, column 1 in row 0, column 2 in row 0, column 3 in row 0. The queen 1 can be placed in row 1 at 4 different columns. So at each level it quadruples. Okay. At each level the number of possible solutions is increases by n times. So here at level 0 we have 4. At level 2 we have 16. At level 3 we have 64. At level 4 we have 256. So for 4 queens we have 256 possible solutions, out of which we have to decide which are all a valid solution. For example, this placement is a valid solution. Basically this is a combinatorial enumeration problem. We can solve this using a recursion. We make a recursive call to place a queen at each row. Okay. For example, we start from here. First we make a recursive call to place the queen at row 0. Then place another recursive call to place the queen at row 1. Then another recursive call to place the queen at row 2. Then at row 4. Basically the height of this call stack will be the number of queens. So this is the two distinct solution for 4 queens. And that's what I have written here. Basically we can solve this problem using recursion with backtracking. And this is a combinatorial enumeration problem. Okay. So first we initialize the count to 0. And then we initialize the slate with an empty slice of int. And then initialize the current row index with -1. Okay. Then we make a recursive call to the helper function with the number of queens and the current row index in which we are going to place the queen, and then the slate to keep track of the queen's position in the previous rows, and then the count. In the helper function, first we check whether the current queen's position is not valid. If it is not valid, we backtrack. Otherwise we go ahead and check whether the length of the slate is equal to n. That means we placed all the queens in all the rows. That means we have a valid solution. So we increment the count. Otherwise we make a recursive call for each column, and in each iteration we create a new current row index by adding 1 to the current row index, and then we append the current column to the slate, and then we make a recursive call to place the next queen in the next row. Okay. We repeat this until we process all the queens, and finally we return the count, which contains the total number of distinct solution for the given input. Let's look at the flowchart. Input for this procedure is the number of queens n and the current row index and the slate, and then the count. First we check whether the current row index is a valid position. Here we call a function which checks whether the current placement of the queen will attack the previously placed queens. Okay. In that case it will return false for the valid position check. Okay. In that case we backtrack. Otherwise we check whether the length of the slate is equal to the value n, the number of queens. That means we successfully placed all the queens, so we increment the count and return. Otherwise we can place the queen in either one of the n columns in the chessboard. By going through this loop, we append the current column number to the slate and then increment the current row index by 1 and assign to the new current row index, and then we make a recursive call with the updated new current row index and the slate, and then count. We repeat this for all the columns. Once we come out of this loop, then finally we return back to the main function where the count will contain the total number of distinct solutions. Let's move on to coding. First I initialize the count variable with value 0 and then initialize the slate with empty slice of int. Then I initialize the current row index with -1. Next I make a call to the helper function with the input n, current row index and the slate and the address of the count. Then finally I return the count variable. Next I am going to write the helper function. First I check whether the current position of the queen is valid. I call the isValid position function with n and the current row index and the slate. If that is false, then I backtrack, return from this function. Otherwise, I check whether the slate's length is equal to n. That means we placed all the queens. So in that case, I increment the count and then return. Otherwise, I write a for loop to place the queen in one of the 4 columns. For each column's placement, I make a recursive call with input n and then increment the current row index and then append the current column to the slate and the count pointer. Next I write the isValid position function. This function will check whether the current queen will attack the previously placed queens or not. If it attacks, then it will return false. So first I initialize the valid variable to true. Then I check whether the current row index is less than 0. This is for the case when the main function calls the helper function. Then I compute the last row index by subtracting 1 from the slate length. Then I process the element from index 0 to the last index in the slate. Each iteration I compare the value at index I in the slate with the value at index current row index in the slate. If both are same, that means the queen is placed in the same column. This is not valid, so I return false. Next I check for the case where the queen can attack others diagonally. For that I compute the row difference and the column difference of the cells in the slate. So find the absolute value of the difference between the index I and the current row index as the row difference, and then I compute the absolute value of the difference between the value at index I in the slate and the value at index current row index. If the row difference and the column difference are same, that means the 2 queens are placed diagonally, which is not valid. So I return false in this case as well. Finally, I return true. Next I write the function to find the absolute value of an integer. If the input number is less than 0, I multiply that number by -1 and return that number. Next I am going to run the test cases. All the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do the code walkthrough with sample input. Input given is n equal to 4. So there are 4 queens. We have to place that queen in the 4x4 chessboard. Okay, there are 2 distinct solutions, so that's why the output is 2. First we initialize the count with value 0 and the slate with empty slice and the current row index with -1. Current row indicates the index of the most recently placed queen. Okay, so -1 indicates we haven't placed any queen yet. First in the total n queen function, the slate is empty and the count is 0 and the current row index is -1. And we make a call to total n queens helper function with the same value. So that's why we see the slate is empty, count is 0 and the current row index is -1. Here we check whether the position of the current queen being placed is valid. Here if the current row index is less than 0, we return that as true. Okay, so we go ahead and check whether the length of the slate is equal to the input value n, which is 4. Okay, next we check whether the length of the slate is equal to n. In this case the slate is empty, so this condition is false. Then we go ahead and place the 0th queen in 4 columns one at a time by calling the recursive function. From this function we place the 0th queen at column 0, okay, and make a recursive call. Here we place the queen at column 1 and make a recursive call. Here we place the queen at column 2 and we make a recursive call to total n queens helper function. Here column 3. So if you look at it, in the called function the slate contains the included value. Basically we append the column to the slate and make a recursive call, right? So we see that in this function 0th queen is at column 0. Here the 0th queen is at column 1. Here the 0th queen is at column 2. 0th queen is at column 3. So in this layer we check the 0th queen is placed in a valid position, okay, by calling the isValid function. And because that the last row index computed 0, so this for loop will not get executed. So this function will return true for all these function calls, okay. And also this, the length of the slate is not equal to 4. So we go ahead and make another recursive call to place the next queen 1 by making a recursive call 4 times, 1 for each column. Here I am just showing only the 2 case where this is the backtracking case, this is a valid position case, okay. For the backtracking case, in this function the slate contains value 1, and when you make a recursive call to place the next queen at column 1, the slate contains 2 entries with value 1. In the valid position function we loop through the slate and check whether there is an entry which contains the value present at the current row index. So in this case 2 entries are having the same column value, so this is not a valid position, so we backtrack. Then we make another recursive call to place the next queen at column 3, okay, and for this case the valid position function return true, and also this is not the length of this slate is not equal to 4. We go ahead and make another recursive call to place the queen 2, okay, at column 0. Okay, so now the slate contains 1, 3, 0 and the current row index contains 2. So for this case also the isValid function returns true because these queens are not attacking each other as per the logic in this function. Okay, they are not in the same column as well as they are not placed diagonally. Then we go ahead and make another recursive function call to place the last queen at column 2. Okay, so now the slate contains 1, 3, 0, 2. In the total n queens helper function again we call the isValid position. For the current slate this function returns true. Next we check whether the length of the slate is equal to input value n. In this case the length of this slate is 4. So we go ahead and increment the count. So the count value will change from 0 to 1. Because we placed all the 4 queens in the chessboard, after incrementing the counter we return back to the total n queens function eventually. Okay, so there is one more distinct solution. When we compute that solution the count will become 2. Eventually we have the output 2 which is an expected output. Next I am going to do the time and space complexity analysis for this solution. Time complexity of this procedure is order of n factorial. Let's take a look at the case 1 where the number of queens is 4. Okay, so without backtracking, after placing the ith queen the number of squares available to place the next queen is n. Basically at every level we have n number of cells in which we can place the queen. Okay, but after that placement that queen may attack the other queens. Okay, but with backtracking, after placing the ith queen, the number of squares available to place the next queen will be n minus I times 2. So at every level we cannot place the queen in I times 2 cells out of n. At level 0 we can place the queen at n cells. At level 1 we can place the queen at n minus 2 cells. At level 2 we can place the queen at n minus 4 cells. It go all the way up to 2. Okay, so it comes to approximately n factorial. Okay, for 4 queens we place the queen at 4 times 2 8 cells. There are two distinct solutions, right? So that's why 4 times 2 cells. Okay, so for n queens it will be n factorial. So that's why the time complexity is order of n factorial. Space complexity is order of n because we allocate space for the slate where we save the information about the queens placed in the previous row, and the maximum size of that slate will be n. And also stack space is used by the recursive function call, and the maximum height of the call stack will be n plus 1. So that's why the space complexity is order of n plus 1. We remove the constant factor out, so the space complexity is order of n. Thanks for watching this video. Have a great day.